What lies at the end of gravity's pull? What happens when a star dies so violently that it tears a hole in the fabric of reality itself? Right now, scattered across our universe, there are objects so strange and powerful that they bend light, slow down time, and challenge everything we thought we knew about existence. These are black holes, and tonight, you and I are going to explore them together. Not with fear, but with wonder. Not with complexity, but with calm curiosity. Close your eyes if you wish, take a deep breath, and let's begin this gentle journey into the cosmos. Before we journey to the black hole itself, let's begin here on Earth, under a peaceful night sky. Look up. Every point of light you see is a star, and each one is a nuclear furnace burning millions of kilometers away. Some are small and steady, destined to fade gently. Others are massive, violent, living on borrowed time. You cannot see it with your eyes, but hidden among those stars are places where light itself cannot escape. Places where the rules of physics become strange and beautiful. These are the black holes, and they have been waiting for us to discover them for billions of years. For most of human history, we never imagined that such things could exist. The idea seemed too strange, too impossible. But in the early 20th century, scientists began to understand gravity in a new way. They realized that massive objects don't just pull on other objects. They actually bend the space around them. Imagine placing a heavy ball on a stretched rubber sheet. The sheet curves and dips beneath the weight. This is what stars and planets do to the fabric of space itself. And if something is heavy enough, if it's dense enough, it can create a curve so deep that nothing can climb back out. But what could be that heavy? What could possibly bend space so much that even light, the fastest thing in the universe, cannot escape? The answer lies in the death of stars. Not just any stars, but the true giants. Stars that are tens or even hundreds of times more massive than our own sun. These stellar titans burn bright and fast, living only a few million years before their fuel runs out. And when they die, they don't fade quietly. They explode in one of the most powerful events in the cosmos. We call this explosion a supernova, and it's in the aftermath of this cosmic violence that a black hole can be born. Let me take you closer to one of these giant stars now. We're approaching a blue supergiant, a star perhaps 50 times the mass of our sun. It's enormous, blazing with a fierce blue light that radiates across light years of space. For millions of years, this star has been in balance. Nuclear fusion in its core generates outward pressure that pushes against the crushing inward pull of its own gravity. It's a constant tug of war, and for now, fusion is winning. But deep in its heart, something is changing. The hydrogen fuel is running low, and the star is beginning to fuse heavier and heavier elements. Inside this star, layer upon layer of different elements are fusing. Hydrogen becomes helium. Helium becomes carbon and oxygen. Carbon becomes neon and magnesium. The process continues, creating heavier and heavier elements, each layer burning hotter and faster than the last. At the very center, a core of iron begins to grow. And here's where the trouble begins. Iron is special. When you fuse iron, you don't get energy out. You actually have to put energy in. So when the core becomes mostly iron, the star's nuclear engine suddenly stalls. The outward pressure vanishes in an instant. And gravity, patient and relentless, finally wins. What happens next is almost too fast to comprehend. Without the outward pressure of fusion, the iron core collapses. All of that mass, roughly the size of Earth but weighing more than our Sun, implodes in less than a second. The collapse is so rapid and so violent that it creates a shockwave that tears back outward through the star's outer layers. This shockwave rips the star apart in a brilliant supernova explosion. For a few weeks, this single dying star will shine as brightly as an entire galaxy. And at the center of all that chaos, where the core once was, something new and strange is being born. In the heart of the explosion, the collapsed core continues to compress. Protons and electrons are crushed together, forming neutrons. The core becomes a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain. But if the original star was massive enough, if there's enough material left after the explosion, even a neutron star cannot hold against gravity's pull. The collapse continues past any known limit. The core compresses down to a point of infinite density. And in that moment, spacetime itself tears open. A black hole is born. Silent, invisible, and profoundly powerful. Now let's talk about what a black hole actually is. You've probably heard that it's a place where gravity is so strong that nothing can escape. That's true, but the reality is even more fascinating. A black hole isn't a hole in the way you might imagine. It's not a tunnel or a doorway. It's a region of space where gravity has become so intense that it has fundamentally changed the nature of reality. At the center is something called the singularity, a point where all the mass is compressed into a space smaller than an atom. But we're not going there yet. First, we need to understand the boundary. This boundary has a name. We call it the event horizon. It's the point of no return. Once you cross the event horizon, you are committed. There is no force in the universe, no rocket engine, no amount of energy that can bring you back. Even light, traveling at 300,000 kilometers per second, cannot escape. The event horizon isn't a physical surface. You couldn't touch it or see it directly. It's more like an invisible line drawn in space, a mathematical boundary where the rules change forever. And for a stellar mass black hole, the one born from a dying star, this boundary is surprisingly small. Let's put this in perspective. If our sun somehow became a black hole, which it won't because it's not massive enough, its event horizon would only be about 3 kilometers across. 3 kilometers. All of the sun's mass, compressed so much that the point of no return fits within the distance you could walk in half an hour. For a black hole with 10 times the sun's mass, the event horizon would be about 30 kilometers across. These stellar mass black holes are tiny compared to the vastness of space, yet their influence is profound. They warp everything around them. Imagine you're in a spaceship, approaching a black hole. From far away, it might be completely invisible. Black holes emit no light of their own. But if there's any gas or dust nearby, you'd start to notice something strange. The material would be spiraling inward, forming what we call an accretion disk. This disk can shine brilliantly because as the gas falls toward the black hole, it accelerates and heats up. The friction between particles makes the disk glow white-hot, radiating more energy than entire stars. This is how we actually find black holes in space. We look for the light from the material falling into them. As your spaceship gets closer, you'd start to feel the gravitational pull. At first, it would be gentle, like the pull of any massive object. But black holes have a peculiar property. The closer you get, the more rapidly gravity increases. This creates what's called a tidal force. If you were falling feet first toward a black hole, your feet would be pulled harder than your head. The difference in gravitational force across your body would stretch you like taffy. Scientists have a name for this process. They call it spaghettification. It sounds almost comical, but it would be intensely real. But let's imagine you have a spacecraft strong enough to resist these tidal forces, and you've decided to approach the event horizon carefully, from a safe distance. You hover there, engines firing to hold your position against the pull. And you start to notice something profoundly strange. Time itself is behaving differently. You've brought a friend in another spaceship who's staying far away from the black hole. You wave to them, and they wave back. But their wave seems to be happening in slow motion. This isn't an illusion. Time near the black hole is actually running slower than time far away. This is time dilation, one of the predictions of Einstein's theory of relativity. Gravity doesn't just pull on objects. It pulls on time itself. The stronger the gravity, the slower time passes relative to an observer far away. If you could somehow survive at the event horizon for what felt like 1 hour to you, decades or even centuries might pass for your friend watching from a distance. The black hole isn't just warping space. It's warping the flow of time. Space and time are not separate things. They're woven together into a single fabric called spacetime, and the black hole is twisting that fabric into impossible shapes. Let's move back to a safer distance now and observe the event horizon from afar. What would it look like? This is where things get truly beautiful. The black hole itself would appear as a perfect black sphere, darker than anything you've ever seen. But around it, you'd see a ring of light. This isn't the event horizon glowing. It's light from behind the black hole being bent around it by gravity. The black hole is acting like a lens, distorting and redirecting light from stars and galaxies behind it. This phenomenon is called gravitational lensing, and it creates some of the most stunning visuals in all of astronomy. To truly understand what a black hole does to space, we need to think about the universe differently. We're used to thinking of space as empty, as nothing. But space is not nothing. It's a real physical thing. Space can bend, stretch, and ripple like the surface of a pond. When you throw a stone into water, you see waves spreading outward. When massive objects move through space, they create ripples in spacetime itself. We call these gravitational waves. And a black hole, being one of the most massive objects for its size, creates the deepest curves and the strongest waves. Picture spacetime as a vast, invisible ocean. Most objects in the universe create gentle dips and curves in this ocean, like boats floating on the water. But a black hole is different. It's like a whirlpool, a maelstrom that spirals down to impossible depths. The closer you get to the center, the faster the current becomes, until eventually you reach a point where the current is moving at the speed of light. That point is the event horizon. Beyond it, the current of spacetime itself is flowing inward faster than light can travel outward. You're not being pulled in by a force. The space you're in is flowing into the black hole. This is what makes black holes so fundamentally strange. They're not just objects in space. They're places where space itself behaves in extreme ways. Light always travels through space at the same speed relative to space itself. But near a black hole, space is moving. So light can be traveling at full speed through space, yet still be carried inevitably inward by the flow of spacetime. It's like trying to swim against a river current that's faster than you can swim. No matter how hard you try, you're swept downstream. Near a black hole, space itself is the current, and nothing can swim against it. The warping of space creates other beautiful effects as well. Light doesn't just get pulled in or bent. It can also orbit the black hole, traveling in circles around the event horizon. There's a specific distance from the black hole, about 1.5 times the radius of the event horizon, where light can orbit in an unstable circle. We call this the photon sphere. If you were at this exact distance, you could theoretically see the back of your own head as light from behind you travels all the way around the black hole and reaches your eyes. Of course, you wouldn't survive to enjoy this sight, but the mathematics are beautiful. Let's zoom out and appreciate the full gravitational lensing effect. When you look at a black hole from a distance, you don't just see one distorted image of the background. You see multiple images. Light from a single star behind the black hole can take different paths around it, arriving at your eyes from different directions. The star appears to be in multiple places at once. If the alignment is perfect, if the star, the black hole, and you are all in a straight line, The star's light forms a perfect circle around the black hole. We call this an Einstein ring, and it's one of the most beautiful phenomena in astrophysics. These lensing effects aren't just beautiful, they're also useful. Astronomers use gravitational lensing to map the distribution of mass in the universe. When light from distant galaxies is bent by closer massive objects, we can work backward from the distortions to figure out how much mass is doing the bending. This technique has helped us discover dark matter, the mysterious substance that makes up most of the mass in the universe, but doesn't emit any light. Black holes, in their warping of space, have become tools for exploring the cosmos. They reveal things we could never see otherwise. As you sit here, thinking about how black holes warp space, take a moment to consider this. The Earth is also warping space right now, just by existing. You're not falling through space toward the Earth. You're at rest in space, but the space around Earth is curved, and that curvature makes you accelerate downward. Gravity isn't a force pulling you. It's the shape of spacetime telling you how to move. Black holes simply take this idea to the extreme. They curve spacetime so dramatically that the geometry itself becomes almost unimaginable. And yet, the mathematics works. The equations describe reality, even in these extreme conditions. Let's imagine something impossible. Let's imagine you've decided to cross the event horizon. You know there's no coming back, but you're driven by curiosity. You want to see what lies beyond that boundary. What would the experience be like? Surprisingly, if the black hole is large enough, you might not feel anything dramatic at the moment of crossing. There'd be no wall, no barrier, no sudden jolt. You'd simply drift across an invisible line in space. But you would know, mathematically, that you've passed the point of no return. The future and the past have fundamentally changed. Outside the event horizon, you always have a choice. You can fire your engines and escape, or you can fall deeper. But once you cross, there's no choice left. All possible future paths lead to the singularity at the center. You can't choose to move away from it any more than you can choose to stop time from moving forward. In fact, inside the event horizon, the direction toward the singularity isn't a direction in space anymore. It's a direction in time. Moving toward the singularity becomes as inevitable as moving toward the next second. This is what we mean when we say nothing can escape. It's not that the gravity is too strong. It's that escape is literally not in your future. But what would you see as you cross? If you look back toward the outside universe, something incredible happens. Due to the extreme warping of light, you'd see the entire outside universe compressed into a shrinking circle behind you. All the stars, all the galaxies, everything outside the black hole would be visible in this circle. And because of time dilation, you'd see time in the outside universe speeding up. Stars would be born and die in moments. Galaxies would spin and merge. You'd witness the future of the cosmos unfolding in fast forward. It would be the last view of the universe you'd ever have. Meanwhile, to an observer watching from outside, something very different would appear to happen. As you approach the event horizon, they'd see you moving slower and slower. Time dilation would make your movements appear to take longer and longer. The light from your spacecraft would shift toward red as the photons lose energy climbing out of the gravitational well. Eventually, you'd appear to freeze at the event horizon, your image becoming dimmer and dimmer, redder and redder, until you fade from view entirely. To them, you'd never actually cross. You'd appear to be frozen at the boundary forever. But that's just how it looks from their perspective. For you, you'd cross in finite time. After crossing the event horizon, you'd continue falling inward. The tidal forces would grow stronger with every passing moment. Remember spaghettification. For a stellar mass black hole, these forces would become unbearable very quickly. But let's imagine you're somehow protected, or that this is a much larger black hole where the tidal forces at the horizon are weaker. You'd keep falling through the interior, and the structure of spacetime around you would become increasingly bizarre. Space and time exchange their roles. The direction to the center becomes your future. There's no stopping it. No turning around. The interior of a black hole is one of the great unknowns in physics. Our equations, Einstein's general relativity, predict that at the very center is the singularity. A point of infinite density and infinite curvature. But infinity in physics usually means our theory is breaking down. It's telling us we don't yet understand what's really happening. At the singularity, our knowledge ends. Quantum mechanics, the physics of the very small, should become important. But we don't yet have a complete theory of quantum gravity. So we can describe the journey to the singularity, but we can't describe what happens at the singularity itself. It remains a mystery. Some physicists think that the singularity might not be a point at all. Perhaps quantum effects, which we don't yet understand, prevent it from forming. Perhaps inside the event horizon, the laws of physics are different in ways we can't yet imagine. There are theories about what might be there. Some suggest a region of highly curved but finite spacetime. Others propose connections to other universes or other regions of spacetime entirely. But these are speculations, mathematical possibilities. The truth is, we don't know. And that's okay. The universe is allowed to keep some secrets. Black holes remind us of how much we still have to learn. Now let's return to the world outside the black hole and explore how these objects behave in the wider cosmos. Black holes aren't just isolated oddities. They're part of the cosmic ecosystem. Many black holes exist in binary systems, orbiting a normal star. The star and the black hole dance around each other, held together by mutual gravity. And as they orbit, the black hole's intense gravity can pull material from its companion star. Long streams of gas spiral from the star toward the black hole, forming that brilliant accretion disk we discussed earlier. These systems shine brightly in X-rays, beacons that astronomers can detect across the galaxy. These binary systems are how we've discovered many stellar mass black holes. The black hole itself is invisible, but we can see its effect on the star. We watch the star wobble as it orbits an invisible companion. We measure the speed of that wobble and calculate how massive the companion must be. If it's more than about 3 times the mass of the Sun and we can't see it, we know it's likely a black hole. Over the decades, astronomers have found dozens of stellar mass black holes this way, quietly lurking in binary systems across our galaxy. But binary systems aren't stable forever. As the two objects orbit, they emit gravitational waves, ripples in spacetime that carry energy away from the system. This causes the orbit to slowly decay. Over millions or billions of years, the two objects spiral closer and closer together. If both objects are black holes, or if one is a black hole and the other is a neutron star, this dance eventually ends in a merger. The two objects collide and combine, creating a larger black hole. And in the final moments before they merge, they emit a burst of gravitational waves so powerful that we can detect it across the universe. On September 14th, 2015, humanity detected gravitational waves for the first time. Two black holes, each about 30 times the mass of the Sun, had collided over 1 billion light-years away. The ripples from that collision traveled through space for over 1 billion years before reaching Earth. When they arrived, they stretched and compressed space by less than the width of an atomic nucleus. But our instruments were sensitive enough to measure it. That detection confirmed a century-old prediction from Einstein. It opened a new way of observing the universe. We can now listen to the cosmos in addition to watching it. Since that first detection, we've recorded dozens more. Some are black hole mergers. Some are neutron star mergers. Each one tells us something new about the universe. We're learning how common these objects are, how they form, and how they evolve. We're testing Einstein's equations in the most extreme conditions possible. And every time we detect a merger, we're witnessing an event of staggering power. In the final fraction of a second before two black holes merge, they release more energy in gravitational waves than all the stars in the observable universe are emitting in light. For one brief moment, the merger is the brightest thing in the gravitational spectrum. But stellar mass black holes aren't the only kind. Our galaxy, the Milky Way, contains millions of stellar mass black holes scattered throughout its disk. But at the very center of our galaxy, there's something much larger. A supermassive black hole, millions of times the mass of the Sun. Almost every large galaxy seems to have one of these monsters at its heart. They're not formed from collapsing stars. They're built up over billions of years by consuming gas, dust, stars, and other black holes. They're the sculptors of galaxies, their gravity helping to shape the motion and structure of billions of stars around them. We can't visit a supermassive black hole as easily as a stellar mass 1. The nearest is 26,000 light-years away at the center of our galaxy. But we can observe it. Astronomers have watched stars orbiting the galactic center, moving at thousands of kilometers per second. By tracking these stars over years and decades, they've mapped out an invisible mass at the center. That mass is about 4 million times the mass of the Sun, confined to a region smaller than our solar system. It can only be a black hole. We even gave it a name: Sagittarius A star. And recently, we took its picture. How do you take a picture of something that's black? Something that doesn't emit light and is, by definition, invisible. The answer is you photograph what's around it. The accretion disk of hot gas swirling around the black hole shines brightly. And the black hole casts a shadow against that bright background. That shadow is larger than the event horizon itself because light from behind the black hole is bent around it, creating a dark region about 2.5 times the size of the actual event horizon. This shadow is what astronomers set out to capture. And in April of 2019, they succeeded. The project was called the Event Horizon Telescope. It wasn't a single telescope. It was a network of radio telescopes spread across the entire Earth, from Hawaii to Chile to Antarctica. By combining their observations, astronomers effectively created a telescope the size of our planet. They pointed this Earth-sized telescope at 2 supermassive black holes. One was Sagittarius A star in our own galaxy. The other was an even larger black hole at the center of the galaxy Messier 87, 55 million light-years away. And they waited for the universe to reveal itself. The image from Messier 87 was released first. And it was breathtaking. There it was, a dark circle surrounded by a bright, asymmetric ring of light. The shadow of a black hole. The event horizon made visible by the glow of superheated matter falling into it. This black hole is 6.5 billion times the mass of the Sun. Its event horizon is larger than our entire solar system. And we could see its silhouette from 55 million light-years away. It was a triumph of human ingenuity, a collaboration between hundreds of scientists and engineers across the world. Looking at that image, you're seeing photons that were bent by the curvature of spacetime around a black hole. You're seeing light that orbited, partially, around the event horizon before escaping to reach us. You're seeing the glow of matter accelerated to nearly the speed of light by gravity's inexorable pull. You're seeing time dilation and relativistic effects encoded in the shape and brightness of the ring. That single image contains confirmation of so many predictions from Einstein's theory. It's not just a picture. It's a test of the fundamental laws of the universe. And so far, Einstein's equations pass every test. The image of Sagittarius A star, our own galaxy's black hole, was released later in 2022. It's a more challenging target because it's smaller and the material around it changes much more quickly. But the image is similarly stunning. Another dark shadow, another bright ring. This time, the black hole at the heart of our home galaxy. It's been there for billions of years, quietly lurking at the center of the Milky Way. And now, for the first time in human history, we've seen it. Not with our eyes, but with our instruments. We've captured the portrait of shadow and light. These images opened a new chapter in black hole science. We're now observing these objects directly, not just inferring their presence from their effects. We can study the dynamics of the accretion disk in real time. We can measure how fast the black hole is spinning by looking at the shape of the shadow and the brightness variations in the ring. We can test general relativity in strong field conditions. And we're just getting started. As more telescopes join the network and our techniques improve, the images will become sharper and more detailed. We'll watch matter spiraling into the event horizon. But imaging black holes is just one way we study them. Every wavelength of light, from radio waves to gamma rays, tells us something different. X-ray telescopes in space observe the hot inner regions of accretion disks. Infrared telescopes peer through dust to watch stars orbit black holes. Gravitational wave detectors listen to the spacetime ripples from mergers. And optical telescopes track the jets of energy that some black holes shoot across millions of light years. Each observation is a piece of the puzzle. Together, they're helping us understand not just black holes, but the evolution of galaxies, the growth of structure in the universe, and the nature of gravity itself. Some black holes don't just consume. They also create. Material falling into a black hole releases enormous amounts of energy. Some of that energy can be channeled by magnetic fields into narrow jets that shoot out from the poles of the black hole at nearly the speed of light. These jets can extend for millions of light years, far beyond the galaxy that hosts the black hole. They're among the most energetic phenomena in the universe. A black hole with jets is called an active galactic nucleus, and they can outshine all the stars in their host galaxy combined. They're cosmic lighthouses visible across the universe. The mechanism behind these jets is still being studied, but we understand the basics. As material spirals into the black hole, it becomes threaded with magnetic fields. These fields are twisted and amplified by the rotation of the disk, and possibly by the spin of the black hole itself. Eventually, the magnetic fields become so twisted and powerful that they act like a particle accelerator. They grab charged particles and fling them outward along the black hole's rotation axis. The result is a jet of electrons, protons, and radiation moving at nearly light speed. The jets plow through the surrounding space, creating shock waves and energizing the material they encounter. When these jets slam into the surrounding intergalactic medium, they create enormous bubbles and lobes of hot gas. We can see these structures in radio telescopes. They're often bigger than the entire galaxy, extending for hundreds of thousands or even millions of light years. The energy pumped into these lobes by the black hole can actually affect the evolution of the galaxy. It can heat up gas that would otherwise cool and form new stars. In this way, supermassive black holes regulate their own growth. They control the rate at which new stars are born in the galaxy around them. The black hole and its galaxy grow together, locked in a feedback loop. Quasars are among the brightest active galactic nuclei. They're supermassive black holes in the early universe, consuming material at a prodigious rate. A quasar can be thousands of times more luminous than an entire galaxy of stars, yet all that light comes from a region smaller than our solar system. The brightest quasars can be seen from billions of light-years away. When we observe them, we're looking back in time, seeing the universe as it was when it was much younger. Quasars tell us that supermassive black holes existed when the universe was less than 1 billion years old. How they grew so massive so quickly is still a mystery. Blazars are a special type of quasar, where one of the jets happens to be pointed almost directly at Earth. Because of relativistic beaming effects, the jet appears extremely bright. The radiation from a blazar can vary dramatically over hours or days as turbulent blobs of plasma race down the jet toward us at nearly the speed of light. These objects are among the most variable things in the sky. Observing them is like watching a cosmic fireworks display. Blazars are also sources of high-energy gamma rays and possibly even neutrinos, ghostly particles that can pass through entire planets without interaction. It's humbling to think that black holes, objects defined by their ability to trap light, are also responsible for some of the brightest objects in the universe. The energy they release as they consume matter far exceeds the energy produced by nuclear fusion in stars. In fact, accreting black holes are the most efficient engines for converting mass into energy that we know of in nature. Einstein's famous equation, energy equals mass times the speed of light squared, tells us that mass contains enormous amounts of energy. Black holes are nature's way of unlocking that energy. The study of active galactic nuclei and jets has connected black hole physics to cosmology and the evolution of the universe. We now understand that supermassive black holes play a crucial role in how galaxies form and grow. They're not separate from their galaxies. They're integral parts of the system. The mass of the black hole is correlated with properties of the galaxy, like the velocity dispersion of stars in the galactic bulge. This relationship tells us that the black hole and the galaxy must have grown together, each influencing the other's evolution. Black holes are sculptors of cosmic structure. Let's step back even further now and ask a bigger question. Where do supermassive black holes come from? We understand how stellar mass black holes form from collapsing stars. But supermassive black holes are millions or billions of times more massive. They can't form from a single star. The current thinking is that they grow over time. A stellar mass black hole might form first, then gradually consume gas and dust from its surroundings. Occasionally, it might merge with another black hole. Over billions of years, through countless meals and mergers, it grows into a monster. But there's a problem with this story. We've found supermassive black holes in the very early universe, less than 1 billion years after the Big Bang. That's not a lot of time for a black hole to grow from stellar mass to billions of solar masses through gradual accretion. Even if the black hole is consuming material as fast as physically possible, it takes longer than that. So astronomers are exploring alternative ideas. Perhaps some black holes formed directly from the collapse of massive clouds of gas in the early universe, skipping the star phase entirely. These would be intermediate mass black holes, hundreds or thousands of times the mass of the Sun, giving them a head start on growth. Another intriguing idea is that the first black holes might have formed from the direct collapse of exotic matter in the moments after the Big Bang. These primordial black holes wouldn't come from stars at all. They'd be relics from the birth of the universe itself. While most primordial black holes, if they exist, would be very small, some theories allow for a range of masses. If primordial black holes with intermediate masses formed in the early universe, they could be the seeds that grew into the supermassive black holes we see today. It's a speculative idea, but it's one way to solve the timing problem. We're actively searching for intermediate mass black holes to test these ideas. These objects, if they exist, might be lurking in dense star clusters or roaming through galaxies. They're not as easy to detect as stellar mass or supermassive black holes. They don't have obvious companion stars to betray their presence, and they're not massive enough to create the dramatic effects we see in galactic nuclei. But astronomers have found a few candidates. Gravitational wave detectors have picked up signals from black hole mergers, where at least one of the objects is in the intermediate mass range. The picture is starting to come together. Understanding how supermassive black holes formed is important because they're connected to the story of how galaxies formed. The early universe was simpler, more uniform. But tiny fluctuations in density, seeded perhaps during cosmic inflation, grew over time under the influence of gravity. Dark matter clumped together first, forming halos. Regular matter fell into these halos and began forming stars and galaxies. If black holes also formed early, they would have influenced this process. Their gravity would have pulled in more matter. Their jets and radiation would have heated and stirred the surrounding gas. They're not passive objects. They're active participants in cosmic evolution. One of the most profound ideas in cosmology is that we live in a structured universe. Matter isn't spread uniformly. It's organized into stars, galaxies, galaxy clusters, and vast filaments of dark matter forming a cosmic web. Black holes are nodes in this web. They're gravitational anchors. The supermassive black hole at the center of a galaxy helps hold the galaxy together and influences how it interacts with neighboring galaxies. When galaxies collide and merge, their central black holes eventually merge too, creating even larger black holes. The history of black hole mergers is the history of galaxy formation. So as you lie here, thinking about black holes, consider this. You're part of the same cosmic story. The atoms in your body were forged in stars that lived and died before our sun was born. Some of those stars might have become black holes. The galaxy you live in has a supermassive black hole at its center, influencing the motions of billions of stars, including our sun. The universe is vast and ancient, and black holes are woven into its fabric. They're not separate from us. They're part of the same cosmic tapestry. We're all connected by gravity, by time, and by the shared story of matter evolving in the universe. Black holes raise profound questions, not just about space and time, but about the nature of information and reality itself. One of the most famous puzzles is the black hole information paradox. Here's the problem. In quantum mechanics, information is never truly lost. The state of a system at one time determines its state at all later times. But black holes seem to destroy information. Anything that falls into a black hole disappears beyond the event horizon and, we assume, is destroyed at the singularity. Once it's gone, there's no way to know what fell in. The information is lost. But this violates quantum mechanics. So which is right? In the 1970s, Stephen Hawking discovered something surprising. Black holes aren't completely black. Due to quantum effects near the event horizon, black holes emit radiation. This radiation, now called Hawking radiation, is incredibly faint. For a stellar mass black hole, the temperature of the radiation is only a few billionths of a degree above absolute zero. It's far too faint to detect with current technology. But theoretically, it's there. And over unimaginably long timescales, longer than the current age of the universe by many orders of magnitude, this radiation would cause the black hole to slowly evaporate. Eventually, it would disappear entirely. But here's where the paradox deepens. Hawking radiation is thermal, meaning it's random and carries no information about what fell into the black hole. If a black hole evaporates completely into thermal radiation, the information about everything that ever fell in is lost forever. This conflicts with quantum mechanics, which says information must be conserved. Physicists have been arguing about this for decades. Some propose that information is somehow encoded in the radiation in subtle ways we don't yet understand. Others suggest that information escapes in the final moments of evaporation. Still others think we need a new theory that unites quantum mechanics and gravity. One proposed resolution involves the holographic principle. This idea suggests that all the information about the three-dimensional interior of a region of space can be encoded on its two-dimensional boundary. For a black hole, this would mean the information about everything inside is somehow stored on the event horizon itself. The event horizon would be like a hologram, containing all the information in a lower dimensional form. When the black hole evaporates, the information would be released with the radiation. It's a radical idea, but it's been influential in theoretical physics. It suggests that reality might be stranger than we imagine. Black holes also challenge our understanding of causality and determinism. Inside the event horizon, the singularity is not just in your future. It's in everyone's future. All paths lead there. But what does that mean? Does the future already exist in some sense? Is free will an illusion near a black hole? These aren't just physics questions. They're philosophical ones. Black holes sit at the boundary between what we can describe with mathematics and what remains mysterious. They force us to confront the limits of our understanding and to question the deepest assumptions we make about the nature of reality. Some physicists have speculated about the possibility of wormholes, tunnels through spacetime that connect distant regions or even different universes. In theory, a rotating black hole might contain a passage to another region of space. But crossing it would be extraordinarily dangerous, if not impossible. The tidal forces would tear anything apart. Quantum effects might destabilize the wormhole. And even if you could traverse it, there might be no way back. Wormholes remain firmly in the realm of speculation and science fiction. But they illustrate how black holes push the boundaries of what's possible in physics. They make us ask what if. The study of black holes has led to some of the most important developments in theoretical physics over the past 50 years. Attempts to understand them have driven research into quantum gravity, string theory, and the nature of spacetime itself. Black holes are laboratories for extreme physics. They let us test our theories in conditions we could never create on Earth. And every time we think we understand them, they reveal a new mystery. Perhaps that's the most important lesson black holes teach us. The universe is under no obligation to make sense to us. Our job is to keep asking questions and exploring. We've talked about how we find black holes, but let's appreciate for a moment how difficult it is. You're looking for something invisible in the vastness of space. Most black holes are isolated, with no companion star and no accretion disk. They emit no light. They're just there, invisible and silent. The only way to detect them is by their gravitational influence. If a black hole passes in front of a distant star, its gravity can bend the starlight, causing the star to briefly appear brighter. This is called gravitational microlensing. By monitoring millions of stars and waiting for these brief brightening events, astronomers can detect lone black holes. These microlensing surveys have begun to reveal the population of rogue black holes in our galaxy. They drift through space, remnants of stars that died billions of years ago. Most will never interact with anything again. They'll just wander through the galaxy for trillions of years, invisible travelers in the dark. But occasionally, one might pass near a star or a cloud of gas. When that happens, it becomes visible, if only briefly. We get a glimpse of these wanderers, these ghosts of dead stars. And each detection tells us a little more about how many black holes are out there and where they came from. The search for black holes has become a multi-wavelength, multi-messenger effort. Radio telescopes search for jets and emissions from active galactic nuclei. X-ray satellites look for the hot inner regions of accretion disks. Optical telescopes monitor stars for microlensing events and track the orbits of stars around invisible companions. Gravitational wave observatories listen for the ripples in spacetime from mergers. Even neutrino detectors, buried deep underground or in ice, might catch the occasional neutrino from near a black hole. Every type of observation adds a piece to the puzzle. Together, they form a comprehensive picture. One of the most exciting current projects is the search for the black hole in the center of our galaxy as it interacts with its environment. Astronomers have tracked stars orbiting Sagittarius A star for decades, measuring their orbits with incredible precision. One star, called S2, passes extremely close to the black hole. At its closest approach, it's traveling at nearly 3% of the speed of light. By measuring the subtle shifts in the star's orbit due to relativistic effects, we can test Einstein's theory in strong gravitational fields. So far, the theory holds up beautifully. But every measurement refines our understanding. Future missions will push our capabilities even further. The next generation event, Horizon Telescope, will have more stations and better sensitivity, producing movies of black hole dynamics rather than just single images. Space-based gravitational wave detectors will extend our reach, detecting mergers of supermassive black holes across cosmic time. New X-ray telescopes will study the accretion flows around black holes in unprecedented detail. And advanced simulations running on supercomputers will help us interpret the observations, connecting what we see to the underlying physics. The golden age of black hole science is just beginning. There are still many mysteries waiting to be solved. We don't fully understand how black hole jets work. We don't know exactly how supermassive black holes formed in the early universe. We haven't detected intermediate mass black holes in large numbers. We don't have a complete theory of quantum gravity to describe what happens at the singularity. And we're just beginning to explore the role black holes play in the evolution of galaxies and the universe. Each of these mysteries is an opportunity. Each is a chance to learn something fundamental about the cosmos. The questions we haven't answered yet are what makes science exciting. As detection techniques improve, we're finding black holes in unexpected places. There might be a population of intermediate mass black holes in the outskirts of galaxies. There might be primordial black holes left over from the Big Bang, making up some of the universe's dark matter. There might even be tiny black holes formed in exotic processes that evaporate almost instantly. We're learning that black holes come in a wider variety than we once thought. They're diverse, they're common, and they're integral to the universe. Every new discovery expands our cosmic census and deepens our appreciation for the richness of nature. As we near the end of our journey, let's return to where we started. To that sense of wonder you feel when you look up at the night sky. You know now that hidden among those stars are objects that challenge our deepest understanding of reality. Objects that warp space and time, that trap light, that convert mass into energy with terrifying efficiency. Objects born from the death of stars and woven into the structure of galaxies. Black holes are part of the cosmic story, and so are you. The matter in your body was once inside stars. You're made of stardust, and that makes you kin to the cosmos. There's a strange comfort in black holes if you think about it. They remind us that the universe is bigger and stranger than we can fully grasp. They humble us, but they also inspire us. Humans are curious creatures. We've gone from not even knowing about black holes to imaging them, detecting their collisions, and testing the fundamental laws of physics with them. All in the span of a single century. That's extraordinary. It shows what we're capable of when we ask questions and work together to find answers. Black holes teach us about the universe, but they also teach us about ourselves. If you're drifting off to sleep now, that's okay. Let the thoughts settle gently. Imagine floating in space, safe and warm, watching a black hole from a comfortable distance. See the accretion disk glowing softly, like embers. See the stars beyond, their light bent into elegant curves. There's no danger here, just beauty. Just the slow, patient work of gravity shaping the cosmos. Time moves differently near a black hole, and time is moving differently for you now too. Slowing down. Becoming soft and elastic. Let yourself sink into that feeling. You're at peace with the universe. Black holes are patient. They exist on timescales that dwarf human history. A stellar mass black hole can drift through the galaxy for billions of years without encountering anything. A supermassive black hole can sit at the center of a galaxy for the entire lifetime of that galaxy. They don't rush. They don't worry. They simply exist, following the laws of physics, warping spacetime by their very presence. There's a kind of serenity in that, a cosmic patience. Maybe we can learn from it. Maybe we can slow down too and appreciate the moment we're in. Think about the light from distant galaxies, traveling for millions or billions of years to reach your eyes. Some of that light has been bent by black holes on its journey. It's carried information across unimaginable distances. And now it's here, being absorbed by your retina, becoming part of your awareness. You're connected to those distant places by light, by gravity, by the shared fabric of spacetime. The universe is not a collection of separate things. It's a unified whole, and you're woven into it. You belong here. You're part of the patterns. As your breathing slows and deepens, imagine your awareness expanding. You're not just in your body. You're also in the room around you. And beyond the room, the world. And beyond the world, the solar system. And beyond that, the galaxy with its 100 billion stars and its millions of black holes. And beyond that, the universe with its trillions of galaxies, each with its own black holes. You contain all of this in your mind. The universe is out there, but it's also in here, in your thoughts and awareness. You're the universe experiencing itself. Let's rest here for a moment in quiet gratitude. Gratitude for the light that travels across space to show us distant wonders. Gratitude for gravity, which holds planets in orbit and brings us home. Gratitude for the stars that forged the atoms we're made of. Gratitude for time, which flows forward and gives us moments like this one. And gratitude for black holes, strange and beautiful, reminding us that the universe is full of mysteries worth pondering. You don't need to understand everything. You just need to appreciate the journey of discovery. And that journey continues, even in sleep. Our journey to the black hole has come to an end. But the mysteries remain, waiting for future explorers. The universe is vast and strange, filled with wonders beyond imagination. Black holes are just one chapter in the cosmic story. You've traveled far tonight, across space and time, to places where reality itself bends and warps. And now you can rest, knowing that the cosmos continues its slow, patient dance. The next time you look up at the night sky, remember what lies hidden in the darkness. Remember the event horizons, the singularities, the warped spacetime. And remember that you, made of stardust, are part of it all. Until next time, may you find peace under the stars.